of Science Academy's 6-day online lecture workshop organized by the Department of Physics, sponsored by the Indian Academies of Sciences in association with St. Philomena's College Autonomous, Mysore. We have with us Professor G. Umesh to present his lecture before you today. I welcome him, and I also welcome all the participants to today's program.
Good morning, friends. Yesterday, we discussed several aspects which have a connection to the electrical conductivity in metals and semiconductors. And today we will look at an entirely new topic called thermoelectric power. You might have heard about thermo EMF and thermocouples. So what I discuss today will give you an idea about the basic operating principles of thermocouples, and later also I will mention something about what are called as thermoelectric coolers. Okay. Let me remind you that you see we have built a model for metals and semiconductors, and the model for metals and semiconductors really is the following: that we think of both these solids or any solid as a crystal which contains ions at the lattice points and a whole lot of free electrons and holes which are responsible for conduction of electric current in the material. In today's lecture, we will adopt the same model for the solids, and we will discover that there are new phenomena which arise, and what it shows is that the model which we adopt for these solids is quite a useful model, quite powerful, and it helps us to understand the phenomena in a simple manner. So the diagram here shows a rod of a conducting material A, and one end of the rod is heated by using a candle flame or whatever. Okay. So one end of the, let's assume that this is a cylindrical rod. One end of the rod is heated and the other end is not heated, and therefore the other end can be called as the cold end. If this is if this experiment is done, then what happens is that at the end which is getting heated, the energy which is deposited into the material will appear as random motion of the free electrons with increased thermal speeds. Okay, so the electrons at the hot end, free electrons, and the ions as well. So the electrons get hot and the ions also get hot, but we will not worry about the ions. We will worry more about the free electrons in the metal bar. Now, instead of a metal bar, you could also think about having a sample of a p-type semiconductor or a n-type semiconductor. And what I discuss for metals will more or less hold for the semiconductor bars also. Okay. So these electrons which get hot, and the other end, the electrons are cold, and therefore there is a thermal gradient. Okay. Now in thermodynamics, there is something called thermal equilibrium or statistical equilibrium, and this is a very broad principle in physics, and which says that in a medium, if there are gradients of whatever kind, then if it is left to itself, isolated and left to itself, those gradients will, the natural tendency is to kill the gradient. So the gradients will tend to disappear. So if I remove the candle below the bar, what will happen is, because it's a good conductor of heat, the excess heat in the hot end will spread all over the bar, and finally the entire bar will have the same temperature. This is an indication that the gradient has disappeared. Okay. Now, gradients can be of many types. You see, you can have concentration gradient. You can have density gradient. Okay. And in this case, you have a energy gradient or a temperature gradient. Okay. Whenever you have a material at a certain temperature, then you can compute the average energy of the free particles in that medium by multiplying it by Boltzmann constant, as I mentioned yesterday. So talking about temperature or energy is equivalent in a way. Okay. So whenever we have gradients, all right, then left to itself, the medium tries to equilibrate. Okay. So if there is a pressure gradient, then the pressure will tend to spread all over the medium. If there is a concentration gradient, typically like if you light a agarbatti in one end of the room, after some time, even though the agarbatti would have extinguished, the aroma of the agarbatti spreads over the entire room. Okay. So what was high concentration near the agarbatti at one point of time, okay, gradually spreads over the entire room. And this is what we mean by saying the gradient is removed or gradient is killed. So in our experiment here, the same phenomenon, very broad phenomenon, takes effect. And therefore, what happens is that the electrons with larger thermal energy or V thermal, the thermal velocity, will try to move towards the colder end where the electron thermal velocity is less. Okay. So since in a metal, the free particles are electrons, it is the electrons which will move. The hot electrons will move from the hot end of the bar towards the cold end. If that happens, you will immediately realize that more electrons are accumulating at the end where the temperature is T2, the cold end. And since the electrons have left from the hot end acquires a net positive charge. So there is a polarization of the material in the sense that the hot end is more has excess of positive charges, in the sense that the free electrons from there have moved out to the cold end, and the cold end acquires a net negative charge density. So when this happens, as you would easily realize, there's an electric field which is created. Okay. And the electric field tries to oppose the flow of electrons from the hot end. So this is something which sorry, I'll as I have written here, the two ends of the metallic wire are maintained at different temperatures. Free electrons flow from the high temperature end and accumulate at the low temperature end. So the this drift of electrons from the hot end to the cold end results in creation of an electric field or a potential difference between the two ends. And this potential difference tries to prevent more electrons from drifting from the hot end to the cold end. Ultimately, there is a balance which is reached. See, such a thing is also seen in diodes and when you apply a potential. So this is quite similar to that. When the balance is established, we see that if you take a voltmeter and measure, you will see a potential difference between the hot end and the cold end. So this is the basic physical phenomenon that happens, and it happens because of temperature gradient which is created by supplying energy to the bar at one end. Okay, gradients cannot be created in steady state. You have to disturb the steady state by providing energy from outside. So that is what the small candle is doing in the figure. Okay. Right. So if we measure the potential difference between the two ends, the hot end and the cold end, we can show that this potential difference is linearly proportional to the temperature difference. Okay. So one may write this equation, delta V is some constant S times delta T. Later, it is a I will show that it's a convention to put a negative sign on the right-hand side. Okay, we will see the reason for that. Anyway, what is indicated here is that the potential difference is proportional to the temperature difference or temperature gradient. Okay, this constant S is what is called as the absolute thermoelectric power or the Seebeck coefficient. Okay, so this was a phenomenon which was discovered by a scientist by name Seebeck. I will mention about his work a little later also. And what we have discussed happens in the case of metals. Now, the same thing can happen with semiconductors also. And we will see that such a development of a potential difference by supplying heat at one end of the sample is seen in both p-type and n-type semiconductors. This point which I have written here, generally S increases as temperature increases. Please ignore it because it is seen in metals, but not over the entire temperature range. And plus in some metals, it is also, it decreases with temperature. So I will make this point more clear a little later. Okay, so don't take this very seriously. The next sentence is about semiconductors. In semiconductors, the carriers at the hot end not only have larger thermal energy. Look at this, difference between metal and semiconductor. If you heat a semiconductor, you know that the carrier density will shoot up. Okay, it will shoot up according to the exponential law which we learned yesterday, right? And therefore, the heating of one end of the semiconductor not only adds kinetic energy to the free carriers, but it also increases the number of free carriers. Okay, this is because the donors start contributing heavily to the conduction electrons in the conduction band. So carrier diffusion can now happen due to both these gradients, the temperature gradient and also the concentration gradient. Okay, so semiconductors behave a little different from metals. One of the things that we should keep in mind is this Seebeck coefficient cannot be measured for a single material directly. Okay, we have to do experiments with pairs of different materials. Essentially, we have to make a thermocouple and then measure Seebeck coefficient of one metal with respect to relative to another metal. We will come to that a little later. All right. So Seebeck coefficient or absolute thermoelectric power is the potential difference which develops because of temperature gradient. Please note that the value of Seebeck coefficient S, okay, is a property of the material. Okay, like you have density and then electrical conductivity, thermal conductivity, and so on for different materials. Seebeck coefficient is also a characteristic parameter for a given material. And it is generally seen that the Seebeck coefficient depends on temperature, as I mentioned just a minute back. The definition for Seebeck coefficient is what is given as the third point in this slide. It is defined as minus dV by dt. Okay, as the derivative minus dV by dt. And earlier I had mentioned about this minus sign. So that is included in the conventional definition of Seebeck effect. Typically, you have the Seebeck coefficient in microvolts per degree Kelvin. Okay, so if you increase the temperature by a degree Kelvin, then the increase in the potential difference across the two ends would be 1 microvolt. But there are semiconductors in which this runs up to millivolts also. I will mention that a little later. The sign of S represents the potential of the cold side with respect to the hot side. Okay. The significance of this I will describe very shortly. So suppose I take an N-type semiconductor. It has excess, the carrier types are electrons in the conduction band. And if I supply heat to one end of a N-type semiconductor bar, then electrons diffuse from the hot end to the cold end. Okay. So the cold end becomes more negative compared to the hot side. Okay. So yes, and therefore, in such a case, we say that S is negative. Another way of looking at it is as follows. You see, look at the equation S of T equal to minus dV by dt. If I am heating the material, then dt will be positive. Okay. And dV we count as positive if the hot end is at the higher potential than the cold end. Okay. Now, this is the case in N-type semiconductor because the electrons diffuse away from the hot end. So essentially, the hot end is more positive and the cold end is more negative. Okay. So dV in such a case conventionally is taken as a positive number. Therefore, both dV and dt are positive and therefore S is negative. In other words, what you can say is, in the case of N-type semiconductor, S is negative. In the same manner, if I take a P-type semiconductor, then the dominant carrier types are the holes. And if you heat one end of a P-type semiconductor, it is the hot holes which will diffuse towards the cold end. So what happens is that the hot end becomes more negative compared to the cold end. And in this case, as we argued for N-type, in this case, delta V will be negative and therefore S will become positive. So in short, what you can note is, if you have an N-type semiconductor bar and you heat one end of the bar and cool the opposite end, then the Seebeck coefficient has a negative value. In a P-type semiconductor, Seebeck coefficient S is a positive quantity. If you remember that, it is sufficient. Now, one can also note that S is positive when the direction of the current flow is the same as the direction of heat flow. Okay. Now, this you can see from the example of a metal or an N-type semiconductor, which I mentioned. All right. In the metal, it is the electrons which are moving from the hot end to the cold end. Therefore, the conventional current is in the opposite direction. Okay. And heat flows from hot end to the cold end. Therefore, the direction of electric current and the direction of heat flow is opposite. Therefore, S is negative. That is another way of looking at the sign of S. Okay. All right. I mentioned that Seebeck coefficient cannot be measured if you have a single sample. It can be measured only if we do an experiment with a pair of different materials, different metals. So typical device which is used to measure thermoelectric voltage, EMF, is a is a junction which is formed with two different metals, which is generally referred to as a thermocouple. Okay, so this figure here, it shows a wire of type A and a wire of type B, and there are two junctions. All right. In the wire B may be connected to a voltmeter, or it may be just connected without a voltmeter. All right. The left side junction is shown to be at a higher temperature. So the left side junction is heated, and the right side junction is lower temperature. So it is the cold end. Okay. If I don't have the voltmeter, and if the wires B and B on the left and right are connected, joined together, then we expect a current to flow in the circuit. Okay. Now, normally, whenever you want to make a current flow in a circuit, you have to connect it to a battery which supplies the energy for driving the current. In the present case, the energy is supplied by the source which is supplying heat to the hot end. Okay. So this external energy input into the device results in the flow of current. Why is the current generated? The current is generated because of the potential difference which is established between the hot end and the cold end. Okay. And this potential difference for a device in which a pair of metals or materials are used is given by delta V equal to minus SA minus SB times delta T. Okay. So, where SA is the Seebeck coefficient of material A and SB is the Seebeck coefficient of material B. You will immediately note, okay, before I go say what I was about to say, if I break the wire B in the middle and connect it to a voltmeter, I will measure this voltage drop delta V, okay, the potential difference. Okay, so in an actual experiment, we do measure such potential difference in all thermocouple experiments. What I was going to say was that in the experiment which is shown, if instead of the material B, wire of material B, I use the same material as A, you will immediately see that delta V will go to 0. Because if SB is also SA minus SB gives you 0. So if you make a circuit with the same material, wires of the same material, of course, then the question of junction is a bit trivial. You are making a junction, so-called junction with the same material. All right. Keep one end hot and the other end cold. You don't see any voltage develop. The reason is, see, if you see the figure 1, which you are seeing in the slide, in the wire A, suppose it's a metal, the electrons will flow from hot end to cold end, so it will be a clockwise current in part A. Similarly, in metal B, if there's no voltmeter and if the metals are connected, metal wires are connected, B on the left to B on the right, then the electrons will flow from the hot end to the cold end and the current direction will be anti-clockwise. Okay. So since these two currents are equal and opposite, essentially no current will flow, which implies that the potential difference is 0. Okay. Or in other words, the potential difference which is established by the upper branch is exactly equal and opposite to the lower branch if B is replaced by A. Okay. So you understand why in a thermocouple we must have two different materials making the thermocouple. So as I said before, the ratio delta V by delta T in the limit delta T going to 0 is called the thermoelectric power, and its value is given by SB minus SA. Now, with this formula, you may also note that if I somehow fix the value of SA, then by doing the experiment, that is determining delta V for a certain temperature gradient delta T, if I measure delta V and I also measure delta T and I know SA, then I can evaluate the value of SB. So that is why we say that the Seebeck coefficient can be determined with reference to the Seebeck coefficient of a standard material. So in conventional thermocouples, platinum is chosen as a standard material, and Seebeck coefficients of other materials is determined with reference to the Seebeck coefficient of platinum. Okay. Seebeck coefficient of one takes one of the wires to be platinum and measures the Seebeck coefficient relative to the Seebeck coefficient of platinum. And this is done by making a thermocouple out of platinum and the other material. Seebeck coefficient of copper and constant N. See, these are materials which are normally used for making thermocouples. So you may make a note of it. Platinum, copper, constant N, chromel, alumel. There are these materials. I'll give you show you a slide where there are some more materials mentioned. Semiconductors can also be used to make thermocouples. But usually you would have used thermocouples made of metals. So if the Seebeck coefficient of copper and constant N as determined by the principle I just now spoke, if they are 6.5 and minus 35 microvolt per degree Kelvin, okay, and if we form, see, earlier we were talking about a thermocouple made of platinum and maybe copper, or made of platinum and constant N. Okay, by doing those experiments, you can determine the Seebeck coefficient of copper and constant N. Now, if you make a thermocouple of copper and constant N, then it can be easily seen that the effective thermoelectric power would be 6.5 minus of minus 35, because it's something like SB minus SA. Okay. So that will give you a value of 41.5 microvolt per degree Kelvin. Okay. So if we, for some reason, if we want to have a large Seebeck coefficient, by choosing materials properly, we can achieve that target. Okay. Once again, I must mention that thermo power S or Seebeck coefficient will depend on temperature, will vary with temperature. Okay, as I said, Seebeck effect was discovered by a German physicist, Thomas Johann Seebeck, in 1821, long back. Okay, before people understood many other things, Seebeck was able to discover that when using a conductor, okay, semiconductors came much later. When using a conductor, if it is subjected to a thermal gradient, it will generate a voltage. And as I said, if you make a continuous circuit of two different wires of two different materials, which will involve two junctions, you can refer back to the previous figure, remove the voltmeter, and make a continuous circuit. Okay. In such a case, a current will flow because of the heat energy supplied. To make the current flow, you must have wires of two different materials. Okay. And when you have material wires of two different materials, essentially you will be using materials with two different Seebeck coefficients, and therefore a voltage will develop. So different metals, different metal alloys, semiconductors are used in making thermocouples. And we will see that the Seebeck coefficients vary over a wide range of values. And Seebeck coefficient can be positive, negative, and it can vary with temperature. And Seebeck coefficient is positive when the direction of current, electric current flow is the same as the direction of heat flow, as I discussed a while earlier. Okay, I think this we have discussed. All right. Let us now come to Seebeck effect of semiconductors. Okay. We will see later that, determination of formula for calculating Seebeck effect involves a detailed analysis of the band structure of the material. Okay. So semiconductors can have a complex, rather complex band structure. So these band calculations become quite intricate. Okay. And the theory of Seebeck effect, you have to use the so-called Boltzmann transport equation, which deals with the evolution of this distribution function of the electron gas. And we will not bother about the detailed theory, but we'll quote the equation for determining Seebeck coefficient, which was developed by Sir Neville Mott. Some of you may note that he is one of the Nobel Prize winners. So the Seebeck coefficient is given by the formula which is shown here. Okay. Notice that it is proportional to temperature, and there is also a derivative of the conductivity. We also know that conductivity depends on temperature. Okay, so the dependence of S on temperature can be quite complex. In the above expression formula, this symbol epsilon, we came across this symbol epsilon yesterday also. This is the maximum energy in the conduction band up to which the carriers or electrons are filled. Okay. This will become a little clearer in one of the next slides. Okay. What we are saying is that in semiconductors, you have valence and conduction bands. And there are empty quantum states in the conduction band. So electrons which go from the donor levels or from the valence band try to fill into these vacant energy states in the conduction band. Okay. But it so happens that at a given temperature, most of the electrons will occupy energy levels up to a certain maximum energy in the conduction band. Okay. And it turns out that this value of epsilon in semiconductors is quite small. In the case of metals, it is quite high. Okay. And I will illustrate this with a graph, maybe in the next or the next slide. We know from the theory of solids that electrons having a certain energy, electrons which exist in the conduction band, okay, and which have an energy up to a maximum of this epsilon, those are the electrons which contribute to the electrical conductivity. Okay, the rest of the electrons which are in the valence band are bound. Those electrons in the valence band will not be able to, contribute to electrical conductivity. And the carrier density in the conduction band, okay, depends on the electrical conductivity, sorry, depends on the carrier density, as we saw yesterday, and it also depends on the relaxation time. Okay. Now both these can be temperature dependent. We discussed this extensively in the lecture yesterday. Now in the theory of solids, you can show that in the effective mass picture, or adopting the concept of effective mass, this carrier density is seen to be proportional to square root of the energy. Okay. So if we see this, here is a graph with which you would know this graph. You would be familiar with this graph. It shows the predicted variation of carrier density n of epsilon per unit volume as a function of energy epsilon. This epsilon may not be visible on the x-axis. Okay. What is plotted on the x-axis is the energy. Now we also know that do I have a cursor here? Yeah. We also know that at a certain value of epsilon, you have what is called as the Fermi level. Okay. So in actual practice, this graph will decrease down in for practical semiconductors, and this reduction in the value of n happens close to the Fermi level. Okay. What we should note is that the Fermi level for a metal is quite high. It is of the order of several electron volts, may vary from about 2 to 10 electron volts. Whereas for a semiconductor, typical semiconductor, the Fermi level is much less. Okay, so the graph will go like that and then come down, because the Fermi level is much lower in semiconductors. Fermi level in semiconductors would be less than 1 electron volt typically. Okay, so this aspect you must remember. We will come back to this a little later. So for metals, Fermi level can be as high as from 1 to 10 electron volt, whereas for a semiconductor, the Fermi level would be less than 1 electron volt. Some semiconductors may have Fermi level of slightly greater than 1 also, but it is not as high as 3, 4, or 5 electron volts. Okay. The conduction band is occupied till the Fermi energy and a little beyond. The extent of energy level up to which the electrons occupy the states is determined by the temperature of the electron gas, okay, temperature of the material. So over a energy range equal to Fermi energy plus minus kT, the free electrons can exist. Okay. Now for a metal, we have seen earlier that the free electron density is something like 10 to the power of 22 per centimeter cube. As I mentioned, see, the big difference between a semiconductor and a metal is there is no band gap in metals. So the conduction band and valence band are a single band. There is no band gap. Okay. So the entire conduction band, okay, is available for the free electrons to occupy. So therefore, the free electron density in metals can be shown to be very high, 10 to the power of 22 per centimeter cube. On the other hand, for semiconductors which have a band gap, in the band gap there can be no electrons occupying the states in the energy states in the band gap. Okay, free electrons occupy only a small group of energy states in the conduction band, and therefore the free carrier density, let's say, or free electron density in the n-type semiconductor can be of the order of 10 to the power of 14 to 10 to the power of 19. So I have mentioned a typical value 10 to the power of 16 per centimeter cube, which is something like a million times less than what you have in a metal. Okay. Now one can show that this factor d by de of log of any n of e is something like 1 upon 2 epsilon. Okay. And as I just mentioned, epsilon for semiconductor is quite small. Okay. And therefore 1 upon 2 epsilon will be quite large. If that is the case, just note this factor here, d by de of log of, this is ln is natural log. Okay. Don't take n to be the same as n inside. And what is inside the bracket is the carrier density. Let's go back a few slides. Seebeck coefficient is proportional to this factor. So if this factor is large, then Seebeck coefficient is large. For semiconductors, this factor is large. Okay, that is why we find that for semiconductors, Seebeck coefficient can be quite large. Whereas for a metal, the Seebeck coefficient is something like a few microvolt per degree Kelvin. In a semiconductor, it can be as high as 100 times this value. Okay, so it may, for semiconductors, you may have a potential difference developed, or the Seebeck coefficient in the order of millivolt per degree Kelvin. Okay, the Seebeck coefficient for semiconductors can be of the order of millivolt per degree Kelvin, whereas for a metal, it is of the order of microvolt per degree Kelvin. So I was trying to tell you about the number of conduction electrons available in metal and semiconductor. The difference is illustrated in this slide. This slide applies to a semiconductor, N-type semiconductor, let us say. In the theory of solids, you know that you have something called the distribution function, and then you have something called the density of states. The first graph on the left shows the density of states in the conduction band. Okay, because we want to look at conduction electrons or carriers which contribute to transfer to electric current in the sample. So we will bother about density of states in the conduction band. This is the variation is as square root of E, okay, which we discussed a little earlier. And the middle graph shows the probability of occupancy of the different energy states, which is the Fermi-Dirac distribution function. For semiconductors, the distribution function for carriers for different energy levels is described by the Fermi-Dirac distribution function. The nature of the Fermi-Dirac distribution function is what is shown here. Okay, so as the graph indicates, as it extends into the conduction band, which is above the Fermi level, okay, it reduces to 0. Okay, in the valence band, of course, there would be a band gap in between. In the valence band, the value of the Fermi function or Fermi-Dirac function is equal to 1, because all states are occupied in the valence band. A few states are occupied in the conduction band. Okay, so when you want to calculate the number of free electrons in the free electron density in the conduction band, you need to multiply these two graphs and integrate it over the range of energy. Then you will get the graph shown on the right side. This blue part gives you an idea of the the density of conduction electrons. Okay, by the word conduction electron, we mean electrons which will contribute to the conduction of electric current. Okay, so you can see that this is quite a small, the area under this graph will be proportional to the density of the conduction electrons, and you see that it is quite small. In the next graph, we will see the same thing for a metal. You see, in a metal, there is no band gap, okay? And not only are all the levels up to Fermi level occupied, but levels even beyond Fermi level will be occupied, okay? And all these electrons will be available for conduction, okay? Because there are a whole lot of empty states above for at larger energies, okay? So because of this, at a given temperature, what we see is, again, you multiply these two graphs and then integrate, and you get the density of free electrons. You see that all this region in blue corresponds to the electrons which are available for conduction. But at a given temperature, the electrons shown in the slightly darker blue part, okay, they will have more energy and they will be more free, and therefore they will contribute to the flow of current. Okay. Now you can easily see that this area is much larger than compared to the case of semiconductors. Okay. So that is why that is the big difference between metals and semiconductors. So Seebeck coefficient is expressed in units of volts per degree Kelvin. Typically, the value for practical materials are either microvolt per degree Kelvin or millivolt per degree Kelvin. We don't have materials with 1 volt per degree Kelvin kind of materials. Some of the materials and their Seebeck coefficients are depicted in the slide which I am going to show you. On the vertical axis is shown the value of the Seebeck coefficient, and you see that for practical materials which are useful for making thermocouples, you have semiconductors which have Seebeck coefficient of the order of 10 to the power of -3. Okay, 10 to the power of -3 is a millivolt, so it's like a few millivolts per degree Kelvin. If you look at bismuth, it is something like 10 to the power of -4 or 0.1 millivolt per degree Kelvin. If you look at silver, gold, and copper, it is 10 to -6, which is something like a microvolt per degree Kelvin. Okay, so this diagram here gives you an idea of the Seebeck coefficient for different materials. Metals have the smallest Seebeck coefficients. Highly conducting metals have the smallest. Then semi-metals like bismuth and their compounds, they have somewhat larger Seebeck coefficient. And semiconductors have really large Seebeck coefficients of all the materials. Okay, so very often we will see that in making the so-called thermoelectric cooler, it is useful to use semiconductor materials rather than metals. On the other hand, to measure temperatures where we use thermocouples, we prefer to use metals, and so the choice of the material depends on the purpose at hand. Okay. It is, as I said, Seebeck coefficient S depends on temperature. So it is good to know how temperature affects Seebeck coefficient. If you look at an N-type semiconductor, the carrier density increases with temperature. Okay, so at the hot end, the carrier density will increase. And more the number of carriers, smaller is the Seebeck coefficient, which the correlation is seen in the previous diagram. You see, metals like copper, gold, and silver have very high very high carrier density, free electron density, and their Seebeck coefficient is very low. In the case of semiconductors, you can adjust the carrier concentration by doping. Okay, and therefore one can design a semiconductor to have a certain value of the Seebeck coefficient. Okay, the carrier concentration with semiconductors is certainly much lower than that for metals. Okay, so in N-type semiconductor, as the carrier dense, as the one end of the semiconductor is heated, its carrier density goes up because of ionization of the donor levels. And as the carrier density goes up, its Seebeck coefficient can get reduced in the hot portion. Whereas in a metal, even if you heat the metal, the carrier density will not change because it's already very high. And increase the carrier density in metals, you may have to take it to rather large temperatures, which may not be necessary in a practical device. Okay. The temperature dependence of Seebeck coefficient is shown in some of the graphs which will follow. Graph A shows the temperature dependence of some metals. Graph B shows temperature dependence for N-type silicon or N-type semiconductor. And C shows, graph C shows temperature dependence for P-type semiconductor. So let's take a look at that. If you see, take metals Seebeck coefficient, which is typically in microvolts per degree Kelvin, okay, shows a temperature dependence which is seen in this graph. Notice that, for instance, if you take lead, its Seebeck coefficient is slightly negative. Okay. If you take platinum, then for instance, let's say even at room temperature, the Seebeck coefficient is positive, and if you increase the temperature, the Seebeck coefficient becomes 0 at some point and then becomes negative and decreases. So the Seebeck coefficient for platinum and palladium, both of them may be positive at room temperatures, but as you increase the temperature, their Seebeck coefficient goes through 0 and becomes negative. This leads to what is called as inversion temperature with thermocouples made using platinum and palladium. Okay, you can link this to the occurrence of inversion temperature. On the other hand, if you take highly conducting metals like silver, gold, and copper, the Seebeck coefficient is always positive over a wide range of temperature. See, normally we don't have to go beyond 1000, even 500. Okay, so this 1000, 1500 are extremely large temperatures. Extremely large in the sense that we don't normally encounter such temperatures in applications or devices. So for all practical purposes, highly conducting metals have a positive Seebeck coefficient, and it is almost constant for gold. It increases with temperature a little bit for copper, and the increase for silver is a little more. Okay. Other materials like, say, tungsten have a very interesting behavior. The Seebeck coefficient is positive for a large temperature range, so also for molybdenum. But these show a maximum value for Seebeck coefficient. Okay. So we see that the temperature dependence is not a simple thing for metals. And the reason for that is the band structure of those metals. Okay. So complex band structures imply that we have to carry out very detailed of the band structure in order to evaluate the Seebeck coefficient. Remember the formula for Seebeck coefficient derived by Mott, and you will understand what I'm trying to say. Okay, so this is for metals. Let us look at N-type semiconductor. Okay. On the y-axis is plotted the Seebeck coefficient, and on the x-axis is the temperature. Okay. If I look at the magnitude, we note that the magnitude decreases as we go up on the y-axis. Okay. So this magnitude at the of minus 0.4, this magnitude is less than, say, 1. So what we see is the doping concentration is mentioned here. This doping concentration gives us an idea about the possible conduction electron concentration in the conduction band. So we can take this number to be the density of the electrons in the conduction band for N-type semiconductors. So the first lowest value mentioned here at the bottom is 10 to the power of 15. Then next we have 10 to the power of 16, then 10 to the power of 70. So the conduction electron density is increasing upwards. Okay. As it increases, conduction density, carrier density increases, we see that the Seebeck coefficient magnitude decreases. Okay. What is important is the magnitude. So we see that the magnitude decreases as the carrier density is increased. This is one aspect of a N-type semiconductor. Secondly, if we look at a particular semiconductor with a certain doping density, say 10 to the power of 17, the Seebeck coefficient gently increases as the temperature is increased. Okay. So these are the two aspects which we note from this graph. One is variation connected to the doping density. Higher the doping density, lesser is Seebeck coefficient. And secondly, as the temperature increases, Seebeck coefficient also decreases. Sorry, I might have wrongly said that this is increasing. This is not increasing because magnitude of Seebeck coefficient is decreasing as you go up. So the Seebeck coefficient is also reducing as the temperature goes up. What I said a little earlier was not correct. What I said about the variation with doping density was correct, but temperature variation also shows that the Seebeck coefficient decreases as you increase the temperature. So this is the behavior for N-type semiconductor. Let's look at the graph for P-type semiconductor. In the case of P-type semiconductor, you see the opposite. Of course, in P-type semiconductor, Seebeck coefficient is positive. Now, you see the value decreases as we go downwards. So you have to carefully see the values on the x and y axis. Okay. In the previous graph, the value was reducing as I moved up. Here, the values of Seebeck coefficient will decrease as you move down. Okay. So with rise of temperature, we see that the Seebeck coefficient reduces. Okay. And as the doping density is, you see here, doping density is reducing downwards. So this is 10 to the power of 15. This is 10 to the power of 17, 18, and 19. So as the doping density increases from 10 to the power of 15 to 10 to the power of 17, 10 to the power of 18 or 19, the Seebeck coefficient keeps on reducing. Okay, you can look at the point shown here as the doping density at a doping density of 10 to the power of 15, Seebeck coefficient may be about 1.5. If you change it to doping density to 10 to the power of 16, then it reduces from 1.5 to 1.3. Okay. Further, with increase of temperature also, the Seebeck coefficient reduces. So this is the behavior for a P-type semiconductor. in general, we will note that the temperature variation of Seebeck coefficients for more complex semiconductors like binary or tertiary semiconductors is quite complex simply because of the complex band structure. And evaluation of the Seebeck coefficient using Mott's formula depends on the detailed band structure, and which can be quite complex for metals and more complex semiconductors. I will take a break here, and you can also take a 5-minute break and come back again. Thank you. Yeah. Do you also teach here?
Yes.
To undergraduates or
Postgraduates.
Howda? Normally, what do you teach?
Sir, I teach condensed matter physics.
Howda?
Yes.
So,
nanomaterials I teach. Semiconductors so far I have not taught.
no, thermoelectric materials.
I'll be doing, I was teaching band theory of solids, free electron theory of gases. For metals I was doing.
Good.
This one I have not taught in the class.
Yeah, so here is something which you can look at.
Yes.
In fact, even in terms of project, mute ಮಾಡ್ಬೇಕಾ?
Mute it.
we change this slide? Okay. Okay. All right. So we'll resume. So all this while we were talking about the role of conduction electrons or holes in the thermo EMF phenomenon. Okay. Now here is a slightly different angle to it. Very interesting though. We'll now look at what happens to the ions in the solids. Okay. In yesterday's lecture, I told you that if you disturb the ions, it constitutes excitation of phonons. Okay. Now here what we are doing is we are supplying heat energy, and therefore we not only the electrons but the ions will also start vibrating a bit. This results in generation of phonons or acoustic waves. Okay. And higher the temperature, greater is the vibration of the ions, and we interpret that as increase in the phonon density. Okay. So now you will have a phonon concentration gradient. Okay. Earlier we had a hot electron concentration gradient. The electron energy was higher at the hot end and lower at the cold end. And now we have this interesting thing that even phonons, which phonon density becomes high at the hot end, and it is not so high at the cold end, and therefore there is a gradient of phonon density. Now this can cause a diffusion. Okay. And since the electrons interact with the phonons, and because of scattering, okay, this diffusion of phonons, okay, which implies transfer of acoustic energy from the hot end to the lower end, this pushes the electron a bit and adds to the mobility of the carriers. Okay. So we therefore adopting the phonon model, okay, we see that phonons can be transferred from hot end to the cold end. Carriers scatter by interaction with the phonons, and because of this carrier scattering of electrons by phonons, and the phonons being drifting along from hot end to the cold end, a certain drift velocity is contributed to the conduction electrons or the carriers because of the phonon drift. This phenomenon is what is called as phonon drag. That is a drag force acting on the conduction on the free carriers due to the phonon diffusion. Okay. The strength of this scattering or electron-phonon interaction is very interestingly seen to be related to the superconducting transition temperature for metals. Okay. See, you can have phonons both in semiconductors and metals. In particular, if we look at metals, many metals show superconducting transition at very low temperatures. Okay. And very interestingly, this experiment, which is done at rather room temperature or higher, okay, it gives us a parameter to get a measure of the superconducting transition temperature. Okay, so the strength of this electron-phonon scattering, okay, in the metal gives us an idea of, gives us a measure of the superconducting transition temperature for metals. Stronger the electron-phonon interaction, higher is the superconducting transition temperature. Okay. It is seen for lead that superconducting transition temperature is of the order of 7 degree Kelvin for lead. Okay. And as you know, there is always a search for materials with a higher superconducting transition temperature. So this is an interesting point to be noted. However, for copper, silver, gold, highly conducting materials, it is seen that they don't exhibit superconductivity. And one can trace this to the fact that in metals, the electron-phonon interaction can be quite weak. Okay. All right. So phonons drift from high temperature end to the low temperature side. And because the electrons scatter from the phonons, this drift of the phonons gives an additional drift velocity to the from high temperature end to the low temperature end to the electrons. Okay. The electrons are already drifting towards the cold end because of the temperature gradient. To that, the phonon drag also adds a bit to increase the drift velocity. Okay. So this therefore contributes to thermo EMF. But this thermo EMF is not very large. One thing that is seen is that this contribution varies as T to the power of 3, where T is the temperature. At low temperatures, T much less than the Debye temperature, okay, that is the low temperature regime, the contribution of phonon drag scales as T cube. At high temperatures, that is T much greater than Debye temperature, the phonon drag contribution varies as 1 by T. Okay. This variation indicates that there would be a maximum, okay, and the maximum is reached roughly at a temperature around theta d by 5. This is what is seen in for metals. Okay, we will not worry about phonon drag because its magnitude is not much. The next topic which we want to discuss is what is called as Peltier effect. We will see later that this Peltier effect can be exploited to make electronic coolers, okay, which are called as thermoelectric coolers, okay, or Peltier coolers. In 1934, a physicist by name Jean Peltier, he was also it seems a watchmaker, and what he found was that when a current is passed through junction of two dissimilar metals, okay, take two dissimilar metals, make a thermocouple out of it, so it will have a junction, and if we pass a current through such a device, then it is seen that either heat is absorbed or heat is given out at the junction depending on the direction of the current. Okay. If you have the current flowing in one direction in one experiment, you may observe that heat is absorbed by the junction. Okay. So the surroundings get colder because heat is taken away by the junction. If you reverse the current, the same junction may emit heat. Okay. Now this is very, very interesting because normally what you observe is if you take a wire, copper or any other metal wire, okay, if you pass a current through the wire gets hot. This is the natural outcome of an experiment of that kind. Whichever be the direction of current flow in the wire, it works like a heater. It will generate heat always. And this generation of heat is irreversible. Okay. So normally in a wire which may be a conducting wire or a resistive wire, you have an irreversible generation of heat when you pass a current through it. But if you make a junction of dissimilar metals, then at the junction, please note, at the junction, you can observe either absorption of heat from the surroundings or generation of heat at the junction, depending upon the direction of the current flow. This was what was observed by Peltier in 1834. Remember that Seebeck effect itself was discovered a little earlier than this. Okay, and it is seen that each metal is characterized by a certain Peltier coefficient. Okay, because the moment you have current flow, you would have a certain potential difference to be applied across the circuit and a certain temperature difference which occurs at the junction. So once again, you have a temperature difference plus a current flow. Okay, so if heat is absorbed in certain instance, then the heat absorbed per unit time, or in the alternate case, heat emitted at the junction per unit time, okay, is found to be this Q is heat flux, okay, is found to be given by the formula below. Q equal to some coefficient pi of material A minus coefficient pi for material B times the current which is flowing. Okay, so the amount of heat transfer is given by the product of a certain constant Peltier coefficient times the current, and we take the difference between this product for two different materials. Okay, so that gives us the value of Q. Please note that this pi is what is called as the Peltier coefficient. It is a function of temperature, and each material has a certain Peltier coefficient. So what all these things are what we said for Seebeck coefficient also. So to that extent, the Peltier coefficient and Seebeck coefficient have similar aspects. Okay. Peltier heat is seen to be, or the heat generated at the junction in a thermocouple device, okay, is seen to be independent of the shape or size or dimensions of the junction. Okay, it doesn't depend upon whether the junction is big or small or has a certain shape. This is very interesting because it allows design of some experiments to determine the Peltier coefficient. Peltier effect arises due to two metals having different electronic properties. Okay, which means that the conduction electrons have different heat capacities. Okay, different heat capacities in the different materials. Now this suggests that one has to look at the theory on heat capacities, okay, of electrons, and so different materials can have different electronic heat capacities. Even though the electric current is same throughout the circuit, the heat flux is different in the two metals. So the previous statement implies what I'm reading out now. Because the heat capacities are different, it follows that heat flux will also be different in the two metals. Okay. So since the heat flow is different in the two metals, a net heat flow will result. Okay, either it is net heat flow to the junction or from the junction. So either the junction will throw out heat or it will absorb heat. It is to be noted, our detailed experiments show that this is not due to any contact phenomenon or contact potential. Okay, it is more due to different heat capacities of the conduction electrons in the two materials. Okay, the next point is what I have already stated. Peltier heat is a reversible phenomenon. Okay, unlike Joule heat. There is a mistake in the word Joule here. It should be Joule. Sorry about that. So heating due to Peltier effect is a reversible phenomenon. If you reverse the direction of the current, a hot junction, instead of being a heat emitter, the junction will become a heat absorber. This never happens with say a heater coil, which whether you pass the current from left to right or right to left, it will always emit heat proportional to I square R, which is what you would have learnt in the earlier classes. Okay. Lord Kelvin was one of the most prolific scientists in the 19th century, that is 1800s. He showed a very interesting connection between Peltier coefficient and Seebeck coefficient. Please remember that Seebeck coefficient is something associated with only heating. One junction is hot, the other junction is cold. Then a potential is developed. Potential difference is developed. In Peltier coefficient, you drive a current through the circuit, and then this results in a thermal heat flow. Okay. And interestingly, Lord Kelvin found he did a lot of work on thermodynamics, and therefore he showed that the Peltier coefficient is equal to the Seebeck coefficient times the temperature of the material. Okay. So this interesting result is due to Lord Kelvin. Incidentally, the value, one of the scales for temperature measurement is Kelvin. So it's the same Kelvin in whose name the unit of temperature is prevalent. So once we have understood this, we see that there is an immediate application of such a device. What we saw was that if you make a junction between two materials, A and B, and if we maintain if we pass a current through the junction, then one particular the junction can either emit heat or absorb heat. Okay. Now what we do is we make a two-junction device with materials A and B. Okay. There are two junctions, each being a junction of material A and B, and we drive a current through this circuit. Okay. Such that, and the flow of current or the design of the device is such that one junction will get hotter and the other junction will get colder. Okay. So you have one junction at temperature T plus delta T and the other junction at temperature T, and a current is flowing. Okay. So the cold junction keeps absorbing heat from the environment, and the hot junction keeps emitting the heat into the environment. Okay. Now what we can do is we can connect the hot junction to a heat exchanger, which can simply be a block of highly conducting metal, to take away the heat which is deposited into the plate, okay, by the hot junction. On the other hand, the cold junction can be pasted on another block of highly conducting metal, and one sees that this block of metal will get cooler and cooler because the junction which is attached to it absorbs the heat from this metal piece. Okay. So you can have a platform which continuously gets cooled and another platform to which the heat is transferred and it emits the heat at that junction, which is thrown out into the outside atmosphere. Okay. So this will function like a refrigerator. The beauty of this device is there are no moving parts. You should compare this device with a domestic refrigerator which you might be using in your homes. In such a refrigerator, you have a compressor and then you have a working gas, freon, and by compressing the freon, the refrigerator is made to generate a cold environment within the refrigerator. But the refrigerator throws out a lot of heat which you feel when you touch the rear of the refrigerator. Okay. So the refrigerator, normal refrigerator, which we use in our homes, they have moving parts, the compressor, and then there is a working gas and so on. In a thermoelectric cooler, there's no such thing. No moving parts. It's very simple to operate. Okay, just drive a current through the circuit, and then it works like a refrigerator. Such devices are called thermoelectric coolers, denoted as TEC, and this is found to have a very wide range of applications. Okay, one thing which I should say at this point is that thermoelectric coolers cannot be said to be equal to a refrigerator, because the refrigerator handles very large heat loads. Okay, you keep so many items inside the fridge. That means those large number of items have to be cooled. This is what is meant by high thermal load. Okay. Using TE cooler, you may be able to cool an electronic device or a chip. It's a very small item. Okay. So thermoelectric coolers are basically low power devices, but they have their own advantages, because when you make a electronic box, you don't want to have a very large, refrigerant system. Okay. So thermoelectric coolers are ideal for electronic devices or electronic boxes where certain electronic components have to be maintained at a certain cold temperature. Okay. One typical example is a laser diode. A laser diode efficiency drops when the temperature of the device goes up, which is not very desirable. So wherever we use a laser diode, and if we want a stable output, light output from the laser diode has to be mounted on a thermoelectric cooler. Okay, which will keep a check on the temperature of the device and keep cooling it. Okay. Such thermoelectric coolers are characterized by, or rather, the materials which are used in thermoelectric coolers are what are called as thermoelectric material. They are characterized by a certain figure of merit, which is described in the formula below. Figure of merit is Z is equal to S square by K times rho. Here is another very interesting formula. Okay. K is the thermal conductivity and rho is the resistivity of the material, electrical resistivity. So the figure of merit is something which depends on the Seebeck coefficient, square of the Seebeck coefficient, upon product of the thermal conductivity and inverse of electrical conductivity. Okay. It is seen that for good quality thermoelectric coolers, we must have Z much greater than about 2 into 10 to the power of minus 3. And it is seen that most of the thermoelectric coolers, they operate from something like 20 to 90 degrees centigrade. Okay. There are several advantages of TE coolers. I've just made a mention of it. If you want to make a practical TE cooler, one pair of junctions is not enough. Many such junctions may have to be pasted to metal blocks. The hot end of the junction to one metal block, all the hot junctions, and all the cold junctions to another metal block. Okay. The hot metal block can be interfaced to a heat exchanger to throw out the heat, and the cold plate is where you mount the device which is to be cooled. Okay. The current should be also, current through the device should also be fixed so that desired temperature is maintained. Okay. Thermoelectric coolers have the advantage that they have no moving parts. There are no use of harmful or gases which have an impact on the environment. And they are also very practical. They have a very large lifetime, in the sense that they can be used for about 20,000 working hours. These are like use and throw devices, but they cannot handle very large heat loads. Thermoelectric coolers with maximum temperature differential of 70 degrees centigrade, they can handle heat load of about 30 watts, and commercially available thermoelectric coolers, they operate at around 5 to 10, 15 volts at about a current of few amperes. Okay. The next topic which we want to look at is how to measure Seebeck coefficient of semiconductors. Okay. Once you have prepared a material, one would like to measure the Seebeck coefficient of that material. Please note that whenever we determine these material constants, the big idea is that you can use the material more efficiently for a certain application. So that is why measurement of all the characteristic parameters of materials is so important. Okay, and that too, accurate measurement of these coefficients is very, very important. For the measurement which we are going to discuss, the semiconductor sample is taken in the form of a thin plate, flat plate, and this plate is sandwiched between a copper cup, which inside which there is a heater. Okay, and on the lower face of the sample, you have another copper plate as forming the base. Okay, so the upper surface of the sample will be heated, and the lower surface will not be heated. It will be in contact with a copper base plate. We will use two chromel-alumel thermocouple junctions. One junction is connected at the hot on the copper cup which carries the heater, and the other junction is pasted on the copper plate which is the cooler plate. Okay. Now each of these junctions, chromel-alumel junctions, will have two terminals, two wires sticking out. We will call the just for discussion, we will say that the chromel wire of the junction which is connected to the hot end, the copper cup carrying the heater. Okay, the chromel wire end is called contact 1. The alumel wire is called contact 2. For the other junction which is connected to the cooler side, okay, the copper plate on the lower side, okay, which is in touch with the other surface of the semiconductor sample. Okay, for that, the chromel alumel wire will be called contact 3, and chromel wire will be called contact 4. Okay, so I hope you get the idea. Unfortunately, I was not able to copy the right picture, and therefore I'm just describing it. All of you will get the lecture notes which are prepared, or maybe you already have it. Please see the diagram in that lecture notes. So one can use a DC millivolt meter to measure voltages between any two terminals. Okay, and the terminals of the DC millivolt meter are designated as A and B. So we can connect A to either contact 1 or 2 and B to whichever contact. So that is how we'll measure the voltmeter. So I hope you understand what I'm trying to say. The heater is turned on, and in a steady state, there is a steady temperature difference delta T between the upper surface of the semiconductor sample and the lower surface. because the upper end is heated by the heater and the lower end is not heated, so it is at the lower temperature. So the procedure is as follows. We connect the voltmeter to terminals A and B, 1 and 2. So A is connected to 1, which is, what is that? Terminal 1 is chromel. Terminal 2 is alumel for the junction at the hot end. Okay. Similarly, terminal 3 is alumel and terminal 4 is chromel. So chromel wires are on the outside. Of the 4 wires, chromel wires are on the outside and the alumel wires are inside. Inside in the sense in between the two chromel wires. So that's the geometry. So we measure we want to measure the thermo EMF for the chromel alumel thermocouple connected to the hot end. Okay. Here, the hot end is the hot copper plate, and the cold end, which is the other side of the wire, okay, that is exposed to atmosphere. Therefore, the cold end temperature is atmospheric temperature. So T naught is atmospheric temperature, okay, or room temperature. Now, according to theory, delta T, okay, the potential developed between the terminals 1 and 2 is Seebeck coefficient times the temperature difference, which is what is shown here. So the temperature difference is the potential difference divided by Seebeck coefficient for chromel alumel junction. Similarly, we can connect the voltmeter to terminals 3 and 4 and measure the voltage between the second junction. Okay, the second junction is also chromel alumel, but here the temperatures are different. You see, you have the copper block which is cooler than the hot end, but there is a steady heat transfer from the hot side to the cooler side, and therefore the temperature of the copper block, which is on the cooler side, is Tc. It is not room temperature. Okay, so between the temperature of this copper block and the room temperature, you have a temperature difference, which is given by the equation Tc minus T0 is equal to V43, the potential difference measured for the second junction, divided by the Seebeck coefficient for chromel alumel. So notice that in both cases seen here, the Seebeck coefficient is for chromel alumel junction. Next, what we do is see, certain junctions are taken as standard. Okay, so we may know the thermopower or Seebeck coefficient of chromel alumel thermocouple. Okay, so from the measured value of V12 and V23, we can calculate you take the difference of the second equation with respect to the first equation. You can easily see that you can get an equation for TH minus TC. Look back, you got one equation for TH minus T naught and another equation for TC minus T naught. Subtract the second one from the first, you will get an equation for TH minus TC. Okay. So if we call that as delta T, then we see that delta T is V12 minus V43 upon Seebeck coefficient for chromel alumel. Okay. One can now measure the potential difference between terminals 1 and 4, which means between the chromel wire of junction 1 with the between 1 and 4, let me see. One is chromal wire of junction 1. 4 is chromal wire of junction 2. Okay. So that is the potential difference one can measure with the voltmeter. And we can see that the thermo EMF due to chromal semiconductor sample junction, and from V14 gives the thermo EMF due to the chromal semiconductor sample. Okay. And from this we get the Seebeck coefficient of chromal with sample, okay, as V14 upon delta T. Okay. So where delta T is given by the equation shown above. And next what we can do is we can also measure the voltage across terminals 2 and 3, and that gives us the Seebeck coefficient of alumel with the sample, semiconductor sample, which is given by difference between the Seebeck coefficient of aluminum and the semiconductor sample as V23 divided by delta T. So by these measurements, V14 and V23, we can get Seebeck coefficients of the semiconductor with respect to alumel and chromal. Okay. And we also have this data that room temperature value for Seebeck coefficient of chromal is about 22 microvolts per degree centigrade. And for chromal alumel, it is something like 40 microvolt per degree centigrade. These are standard values which have been evaluated. So what we do is we plot V14 as measured, okay, against V12 minus V43. Okay. All these voltages were measured as prescribed in the previous slides. So now we can plot V14 versus V12 minus V43. Okay. Now see the equation above in this slide. All right. You have V12 minus V43 in the denominator. Okay. So if we plot this graph, it is seen that you get a straight line. Okay. What we are plotting is V14 on the y-axis for measured for a particular semiconductor sample of an N-type semiconductor bismuth telluride. Okay. Against V12 minus V43 on the x-axis. This yields a straight line graph. Okay. And what we need is the slope of this straight line graph. Okay. The slope of this straight line graph gives us Seebeck coefficient of the chromal with the sample. From the graph, it is seen that the slope has a value of plus 3.3. So we have Seebeck coefficient of chromal of the sample relative to chromal, okay, as 3.3, and therefore S chromal minus S sample can be written as 3.3 times S chromal S chromal alumel. Okay, so this gives us a value of about 132 microvolt per degree Kelvin. Okay, so from the experiment we can determine this value, and therefore we see that S sample is 132, S chromal minus 132. Now S chromal is a standard value which we saw was 22 microvolt per degree Kelvin. Okay, and therefore we get the value of Seebeck coefficient for the sample. Okay, which is about 110 microvolt per degree Kelvin. So it's a very easy method to determine the Seebeck coefficient of a sample, all right, relative to Seebeck coefficient of chromel. Okay, and Seebeck coefficient of chromel may itself be evaluated with reference to a more standard material like platinum. Okay, so this is the procedure. So I have come to the end of the lecture. I will like to mention, let me see, we have another 5 minutes. So let me also mention something called Thomson effect. This is yet another phenomenon which is seen in materials. And it was discovered by Lord Kelvin in 1851. We talked about Lord Kelvin a little while ago. Sorry. Lord Kelvin is also, he goes by the name of William Thomson. Earlier, he was called William, his name was William Thomson, and then he became Lord Kelvin. When we have an electric current flowing through a single conductor, and we also, which are also maintained at different temperatures. So if you maintain both a temperature gradient and make a current flow through the circuit, as shown in the figure here, then we see that heat is emitted or absorbed at a rate of approximately proportional to the product of the current and the temperature gradient. So one talks about a Thomson coefficient, gamma, which is given by the formula below here as amount of heat exchanged, delta Q, divided by the current times the temperature difference. Okay. Please note that this effect occurs in a single metal. Okay, this effect is seen in a single conductor. So, whereas a Peltier effect is something which is seen in a pair of two different materials, and so also the Seebeck EMF. Okay. So I thought I'll just mention this new effect. Thomson coefficient is the ratio of what is defined in the equation here, ratio of delta Q upon delta T, which is per unit current. Okay, so the ratio of the power evolved, heat power evolved per unit volume in a sample for a unit current and a unit temperature gradient. Basic physics associated with thermoelectric phenomenon was discovered by Thomson. It is seen that Thomson effect is very small and not easy to determine experimentally. So that is why often we discuss about Seebeck effect and Peltier effect rather than Thomson effect. So I thought I will just mention it as a matter of additional information for you. So I'm done. Thank you very much. Any questions? I will be happy to answer.
Sir, you have a question.
There is one question here. Can we alter the Seebeck coefficient by applying high pressure? I would not be able to answer it straight away because, see, the way you can alter Seebeck coefficient is to alter the carrier density. So I don't know whether by high pressure techniques you can alter carrier density. Maybe I will check with Professor Srinivasan and come back to you with an answer. This question was by Narsimha Sikur. Narsimha Sikur. Sorry, I can't give you a straight answer for this, but maybe I'll check and let you know. However, what we have learned is that if you want to alter the Seebeck coefficient, you have to play with the carrier density and play with the temperature a bit, but carrier density has a stronger influence on the Seebeck coefficient. All right. Thank you for your patience.
Thank you, sir, for your comprehensive presentation. I also thank all participants for their active participation. Kindly come back tomorrow at 11 a.m. for the last lecture session. The link to attend the sessions will be sent to your registered email IDs. Thank you.